Welcome everyone, my name is Pramod Beesal, and in this video we are going to discuss about the control theory, which is also known as control engineering and control systems somewhere. Okay, now let me tell you one thing here, that control theory itself a huge course, and they run a full-fledged course in a semester of control theory. But now we are going to discuss that from the viewpoint of ESE prelims only, so only the basic and main concepts, that to theoretical concepts only. Okay, so if any of you wanted to have any detailed discussion regarding any topic, then you can directly write to me after watching these videos. Okay, so what is a control system? It is basically a group of components connected together to perform a task. By default, it includes a regulatory system. Okay, so we are having certain components that we have put together, and we have fed certain type of instructions to it, which it is going to perform based upon the input conditions. Okay, so we already know that we can have two type of controls. One, it could be a open loop control, another it could be a closed loop control. Okay, now what are the components of my control system? There will be a controller which is having basically the instructions written into it, that what it needs to do depending upon the input. Okay, then the controller is going to calculate controller is going to process the input based upon the instruction, and it is going to give a command to my actuator. Okay, now what will actuator do? Based upon that command, the actuator will actuate a process. So it will basically execute and a process will occur. So that is my control system. Now if that's all, I mean, if I was having a input here and then I am getting one output here, if that is the system, then it is known as open loop. Open loop means we do not have any system for feedback here. There is no feedback monitoring device. Okay, there is no feedback monitoring that we are having here in case of a open loop. Okay, that must be clear to you. Open loop means no feedback control, I can say. Okay, but let's say I wanted I was giving a input for having some RPM from our motor. Okay, so I said let make my motor RPM as 300. Okay, but I want to know if I got actually 300 RPM or not. So whether my output is equal to command or desired value or not. Okay, so whether it is desired value or not, if I am checking that, and if there is a difference between my output and my desired value, means there is some error in my system. Okay, so if output is not equal to the desired value, then there is some error in my system. And how much is that error? The error will be naturally equal to whatever desired output that I wanted minus actual output. That is the error value. Okay, so I need my system to act based upon this particular error. Okay, so how I am going to measure the error? Based upon a feedback control. So this output is going to be measured by a feedback control device or feedback monitoring device, and it will be fed to a error measurement device, or I can say a differentiator here. Okay, so there is a differentiator. So whatever input that was coming here, it is going to see the difference of this input and this particular output. Okay, so we usually say that this is plus and this is minus. It is not necessary that all have to work in this way only, plus and minus. If in between we are having some disturbance, then we can have plus minus, that sort of signals also we can have. Okay, but in order to calculate the error, what we need is a plus minus only. Okay, so the error will be generated from here, and based upon that error, my controller is going to take action. So let's say I gave a command to make the motor RPM is 300 RPM, but what I got as an output is 298 RPM. Okay, so that will be sensed here. Okay, so desired value was 300, but actual value is 298, means there is a gap of 2 RPM. Means I want my controller to increase the output RPM from 2. Okay, so it will keep on going like that only. So that is a feedback controlling or feedback monitoring. That is why we call it as a closed loop system. Okay, so these two type of systems are possible in our control theory. Okay, so we will discuss about the block diagram in a while. Before that, I want to discuss about the mathematical modeling of the system. Okay, so how exactly we do the mathematical modeling of any system that we are having. Okay, so I will be having some physical system. The most favorite example of mechanical engineers is mass damper and spring system, nothing else. For whole vibration we do based upon this system only. And this control theory also, most of the parts we do either based upon this or based upon the current, if it is for electrical engineering. The subject is common for electrical and mechanical engineering. Now, in order to do the mathematical modeling, we need to apply the conservation of energy or force or the flow rate or the voltage, whatever is our condition. If we are having an electrical circuit, we will apply the conservation of voltage. If we are having flow measurement system like water height and all those things, then we will apply a flow rate conservation. If we are having normal mechanical system, then we will apply the force conservation. If we are having any thermodynamic system, then we will apply a energy conservation. So depending upon what system we are having, we will apply either one of their conservation to get the equation of the system. Okay, so for example, we are having this system here, right? How exactly am I going to apply my force equation? So what I am going to do here, the very first step that I am going to do is this F input is giving me some X, some displacement here. Okay, so there is going to be a force of Kx in this, and there is going to be a force of d into dx by dt in this one, and there is going to be an acceleration of this mass, and all these three forces are coming from F input only. So I can say my F input t is nothing but equal to mass into acceleration, mass acceleration, plus this dampers value, right? So dampers force will be dx divided by dt plus the spring force, that is our kxt. Okay, k into x. Xt means x is a function of time, that's only, nothing else. Now that is our first step. We have calculated the equation of our system. Okay, then find the order of the differential equation and rearrange it. So we have already rearranged it, means highest order, then the lower one, and then the lower one. So we have rearranged our mathematical equation in terms of the order of our differential equation. So what is the order of this particular differential equation? The order is 2. Okay, the order of this particular system, I can say, is 2 here. Now third one is take the Laplace, both sides we will take the Laplace and then solve that particular equation. Okay, so if I take the Laplace here, so both sides I am taking Laplace, so that will, this will give me Fs, whatever my input Fs, that will become m into s square, plus the other conditions I am taking initial conditions as 0. Okay, so I hope and I believe that you already know how to take Laplace and what are the conditions of a Laplace. So by taking initial conditions equal to 0, this will become ms square, plus this will become ds, plus it will become k, right? Into, I am taking my whole x as common, xs, right? I hope you don't have any problem till here. Then what I will do, I need to solve this particular equation for the output. So output can be, output is what? My x. Input is what? My f. Now if I take a ratio here, that is xs upon fs, that is the ratio that I am taking over here, will be equal to, fs upon xs will be equal to 1 upon ms square plus ds plus k. Now I can solve this equation very easily, and I know that you have already done these type of equations in your vibrations course, so I'm not going to go into the details of it. Anyways, you don't need the details for your prelims exam. So this is what known as our transfer function. Okay, so this is what we call as our transfer function. Okay, so transfer function is what? Transfer function is nothing but output divided by our input, and that will be in terms of s. We always write it in terms of s only, the Laplace variable. Okay, now if we look at the basic properties of the transfer function that you can remember, because we don't have enough time to explain all of them, so maybe you can remember them directly. Okay, so it is the ratio of output variable to input variable. We have explained that already, and we have seen one example how to calculate that. It is the property of the system itself, and it is independent of the magnitude and nature of input. Okay, so this particular thing is a property of the system. So after, what is transfer function? Transfer function is ms square plus ds plus k. So this is the property of this function, which is having some mass, some damping coefficient, and some spring value. Okay, and it is independent of magnitude and the nature of input or driving force. This is very important here. In our transfer function, nowhere we have the mentioning of input. Okay, it is independent of input totally. It is the characteristic of our system, the physical system that we are having. Okay, then next one is the transfer function of different systems can be identical. Now this same type of transfer function can be of other systems also. When we take an electrical circuit which is having an inductor and a capacitor and a resistor, we will get similar type of transfer function only. Okay, so we can get same transfer function for many physical systems. So it is not unique to a physical system, or the same transfer function can be held by different type of physical systems also. It does not provide any information about physical structure of the system. By just looking at it, I cannot predict the physical structure of my system. Okay, as I told you, different physical systems also can have same equation, so I cannot identify to which this one belongs. Then if it is unknown, means if my transfer function is unknown, if I don't know the transfer function, then if it is unknown, then it can be established experimentally. Then we can do enough number of experimentations. We can study the variation of output with respect to our input, and then we can establish a relationship between our output and input, and we can calculate the transfer function. At the same time, if it is known, if we already know the transfer function, like we know this equation here, then it can be used to study the dynamic behavior of any system. So you are very much familiar with its use in our vibrations, how we draw the different curves depending upon this equation only, and we calculate our zeta and everything. Okay, so we can use the transfer function to study the dynamic behavior of any particular system. Now it will be applicable for the differential equations which are linear in nature. There are two conditions for it. One, the differential equation has to be linear in nature. Is this differential equation linear in nature? Yes, it was linear in nature. And time invariant. What do we mean by time invariant? Time invariant is for coefficient only. Means the coefficient should be independent of time. So what were our coefficients here? Our mass, our damper, and our spring constant. These were the coefficients, so they should not depend upon time. Otherwise, we won't be able to apply the concepts of transfer function in that particular case. Now, highest power in denominator defines the order of the system. Okay, so whatever is the maximum power of S in our denominator, that will be giving me order of the this system. Now, numerator can have certain values. Don't think that numerator cannot have anything here. Okay, simply whatever is the maximum value of power in our denominator, that is S square. S square is there, means the order of the system is 2. We have already established that here also. I already told you here, right? The order of the system is 2. Now these are the some basic properties of any transfer function that we have. Now we use these transfer functions to make the block diagrams, or we use the block diagrams to make to calculate the transfer function. It's a vice versa thing. Okay, so this is also a block diagram. This thing you see here is a block diagram of our system. Okay, now the basic components of a block diagrams are, as I told you, there is a differentiator here. Okay, differentiator means we use it to take the difference of two inputs that are coming to it. So let's say if A is coming from here, B is coming from here, and it is a plus and it is a minus, then output will be A minus B. Okay, or we can have a summing point also. When we will call it as a summing point, when we are having summation basically. Okay, so we can have it as a summing point, or we can have it as a differentiator. Then this is called as a branching point. What do we mean by a branching point? Means one single value is getting branched into two parts. So here we were having the branching operation here. So the output was going out also to my system, and I am also measuring it, and it is coming back. So there is a branch here. Okay, so that is a branch point or a node of our system. Okay, now let's say how exactly we are going to make the block diagrams for a open loop and closed loop, and how do we write the transfer functions. Okay, so let's say this is my system. RS is my reference value or my input value, reference value only, because input will be generated here then. So it comes here. This is a differentiator, plus and minus. So some constant is there. Just don't worry about that for now. Let's say the value there that is coming here is ES. That is our error value. Okay, after the differentiator, I'm getting an error value. Then whatever comes in these blocks, they are basically multipliers. Okay, what do I mean by multipliers? That here I will be getting ES into GS. Okay, so ES will be multiplied by GS because it is coming into its direction, and that is equal to CS that I have already mentioned here, right? So whatever value is coming out of here, that is equal to CS, and that will also be equal to ES into GS. So I can say this particular system here, CS is equal to ES upon GS. Okay, now let's say I am again taking a branch from here, and then I am again having a multiplier here. Okay, so there is a multiplier. So if CS is coming from here, because there was CS which is coming from here, then here I will be getting CS into HS, because this is a multiplier. So we can have n number of multipliers in our diagram. Okay, we can have series, we can have parallel, we can have anything is possible here also. This is simple logical things only. And let's say I call it as BS. Okay, just a denomination, just a what we call it, a nomenclature. BS I'm calling it. Okay, now when I talk about the open loop transfer function for this particular system only, if you are having this system, what will be the open loop transfer function for this? So in case of open loop, this would have not been going back to this. I would be having right from ES to my BS. Okay, so open loop transfer function of the open loop would be equal to how much? BS upon ES. Okay, BS upon ES. Okay, and I can calculate also. BS upon ES will be equal to what? BS is CS into HS and CS is equal to ES into GS. So BS upon ES will be nothing but GS into HS. Okay, or you can see it directly also, that from here we are going to this point. Means first I am multiplying G, then I am multiplying H. So that is how we can calculate it. S means these are all functions of Laplace variable. We are doing everything in terms of Laplace only. Okay, if I am having a closed loop here, means I am properly using the error function here, then in case of the closed loop transfer function, the transfer function of the closed loop will become CS, because that is my output for the closed loop, right, divided by RS, that is my input here. Okay, so CS upon RS will become my closed loop transfer function. Now if I want to calculate this value, CS upon RS, what will it become? CS is what? ES into GS. Okay, so I will just write those values out here. So this becomes CS is E into G, right? E into G, and E is what? E was R minus B, right? R minus B, and B is what? C into H. C into H. That is my C, right? That is the value of C here, correct? That is the value of C, right? What is the value of C? Whatever error that I am having, that error is R minus B, means R minus C into H. So that is my error, R minus C into H. Then that error is getting multiplied with G, and that is giving me C here, correct? So now I can solve it for C divided by R. So it will become what? RG minus GCH, and C I will bring on this side, so it will become C into 1 plus GH is equal to RG, correct? And then I can say that C upon R, my transfer function, is equal to G upon 1 plus GH, where all of them are function of a what we call it, Laplace variable only. Okay, so that is how we can calculate the transfer functions related to our block diagram, if we are given a block diagram. Okay, now the last topic for the video, that is our classification of industrial controllers. The industrial controllers, we can have 6 type of industrial controllers mainly used. Okay, one, we can have a 2 position or on off controller, so there is no need to explain it. It will be either turning the system on or it will be turning the system off. Very simple, right? Then we can have a proportional control action. Now what do we mean by a proportional control action? Means I will be basically having this sort of system only, that there is a value coming over here, then there is a proportional gain, and then there will be my output. So this is input and this is output. If I talk about the closed loop, I will be having error here, right, and I will be having my output over here. Okay, so the relationship between the error function and the output function is simply proportionality. The proportionality constant can be anything. So Kp is my proportional gain. Kp is known as proportional gain, but it is not necessary that it is a gain. It can have anything, but usually error is always multiplied only. We call it as a multiplier. Multiplier I can call it, or amplifier I can call it, because I am amplifying my value here, right? So it will be also called as an amplifier if this system is there. So what is the basic property of it? That my output, if I denote that with UT, U is my output, okay, and E is my error. So UT is equal to Kp times my error ET, and where Kp we already know, that is our adjustable value. Okay, so Kp is a adjustable gain. Now this system can also be known as an amplifying system, it can be also known as a multiplying system, and so on. Okay. Third type of the controllers that we have are known as integral control actions. So as the name suggests, that we are going to have an integral relationship between our output and our input. Okay. So here basically ut is changing at rate proportional to actuating error. Now you don't have to get confused between our proportional control and our integral control. It was directly proportional and it is proportional to the rate. That is the difference here. Okay, so what will happen here, that ut will be basically equal to or proportional to, so when I apply some proportionality constant, then it will be det divided by dt. That is our system here. Now I can say, what I can say, it will become okay. I've just said it other way. It is at the rate proportional to actuating error. Ut is changed at a rate, so the rate is change of ut. So dut by dt will be there, and it will be ki into e basically. So that will happen here. So I can say that my ut is equal to nothing but, it comes in terms of integration. That is why we call it as a integral system. So et into dt. Okay, so us upon es. Now if I take the Laplace here between u and e, so that will become us upon es is equal to ki upon s. That is the system for a integral control. Okay, so integral control means ut is changed at a rate, so the rate is of ut, not of error. Okay, and ki here is known as our adjustable constant. Adjustable constant, and definitely it is the constant for integration only, nothing else. Now the fourth type of system that we can have is our proportional integration. Okay, so now we are going to combine the proportionality function as well as the integrity function. Okay, so both of them are going to be there, so a proportionality as well as integrity. So ut will be directly given as kp into et. Okay, that is our proportionality part, but that is not all that we want. So kp upon some ti into 0 to 2 et dt. Okay, I'm just telling you because there has already been one question from this particular part in our previous year. Okay, so there is a proportionality part, there is an integration part, and this gives me us upon es is equal to kp, that will become common from both of them, into 1 plus tis. Okay, so ti here is known as integral gain. Integral gain. Kp is what? Proportional gain. Ti is what? Integral gain. Now similarly I can have some systems which will be giving me only PD, means proportionality and derivative sort of things. Okay, so PID we will discuss later. Let's say we have a system which is PD, fifth type of category. Okay, so I am going to write it directly because you have got the hint now what exactly we are doing over here. Okay, so that will be kp et plus, so there is a proportionality part and there is a derivative part, so kp into td de by dt. Okay, and this gives me basically us upon es. U is our output, e is our input, and that is equal to kp times 1 plus td into s, and td is what? Differential gain. Okay, so td here is known as our derivative gain or differential gain. Okay, so I hope that is clear to us, right? Now the sixth system that we can have is PID, that is our last system, means proportionality will be there, integration will be there, and differentiation will also be there. Okay, so what will happen here, that ut is going to be equal to, all three functions are going to come into picture. Okay, so proportionality gain, okay, then integration gain, so kp upon ti into et dt plus differential gain also, so kp td into de divided by dt. Okay, and that will be giving me us upon es will be equal to nothing but kp will become constant, 1 plus 1 upon tis plus tds, and we already know kp is our proportionality gain, integral gain, and derivative gain. Okay, so these are that is all about our controllers that we can have in our industry, usually based upon the control systems. Okay, Now from this part, there have been one question asked about the integral control action in 2019. So this was the direct statement of that particular question, and options were all of them. So this is our answer, right? So that is 2019 prelims question. Well, that's all for this video. In next video, we are going to discuss about the state space representation of our physical systems, controllability and observability, and then we will wrap it up. Okay. Thank you for watching and best of luck for your exam.